Dune is a novel by Frank Herbert that is rightfully considered one of the greatest science fiction works ever written. People love Dune not only for its engaging plot and unique world, but also for the unusual technologies described by the author. For flights over the desert planet Arrakis, Herbert invented a special aircraft, the Ornithopter. An ornithopter is a heavier-than-air flying vehicle that generates lift through flapping motions of a single pair of wings, similar to those of a bird. In this episode, we will try to understand how practical and realistic such a flying machine would be in our world. You are watching the MiliTime Fiction channel. Let's begin. The literary version of the aircraft differs noticeably from its film adaptations. In Frank Herbert's novel, the Ornithopter truly resembled a bird and used a similar method of vertical takeoff. At the same time, the craft was assisted by jet engines, and in horizontal flight it became more like a jet aircraft with variable sweep wings. The wing design was such that even during cruise flight, the Ornithopter still had to perform occasional flapping movements. The vehicle is described as rather fragile. Taking off with too many passengers or too much cargo, as well as a sharp ascent, could easily result in broken wings. In Denis Villeneuve's 2021 film adaptation of Dune, however, viewers were shown not an ornithopter, but an entomopter. Ornithopters imitate the flight of birds, while entomopters copy the flight of insects. In the film, the vehicle has 4 pairs of long, rigid wings resembling those of a dragonfly. Thanks to their rapid movement, the entomopter is able to lift itself into the air. Both ornithopters and entomopters belong to a class of aircraft known as flapping wing vehicles. A flapping wing aircraft is a heavier-than-air flying machine that uses oscillating wings as its primary means of propulsion, similar to birds or insects. Historically, far more ornithopters have been built than entomopters, although most of them never managed to leave the ground due to design flaws or fundamental issues with the concept itself. What seems like a simple motion, a bird's wing beat, turned out to be extremely difficult to replicate. A bird's wings are driven by numerous muscles working in precise coordination, controlled by one of the most advanced computational systems in nature, the brain. Only in recent decades have scientists been able to present drones that partially imitate bird flight. A fully functional flapping wing aircraft capable of carrying a human was built only in the early 2000s. That experimental vehicle had a primitive straight wing divided into 2 segments so that during the upward stroke its surface area was smaller than during the downward stroke. It was not equipped with an engine due to payload limitations, so it was powered solely by the pilot's muscle strength. The aircraft managed to lift off the ground, fly a short distance, and then perform a soft gliding landing. The entomopter from Dune features a far more complex flapping mechanism. In addition to up and down movements, the wings also rotate. For dragonfly-like flight, the wing must be oriented vertically during motion, rotate into a horizontal position at the highest point, and maintain that orientation during the downward stroke. This cycle must be repeated 50 to 70 times per second. From an electronic standpoint, this is feasible, but mechanically, such a system is extremely challenging. If we assume the entomopter has the same mass as a Bell 206 Jet Ranger helicopter, about 2,018 kilograms, then each joint would experience a load of roughly 504 kilogram force at a frequency of 50 cycles per second. This is less than the load experienced by helicopter rotor blades, but there is an important difference. In a helicopter, the load is constant and acts in one direction, while the entomopter's joints are subjected to alternating forces. This leads to much faster wear, even compared to higher static loads. This can be illustrated with a simple analogy. In the first case, a heavy backpack full of books is hanging on a hook. The load is large but constant and directed downward, so the hook can withstand it for a very long time. This is similar to helicopter rotor blades. In the second case, imagine grabbing a door handle and pulling it down, then up, then down again, 50 times per second. Even if the force is smaller than the weight of the backpack, the handle will quickly loosen, start creaking, and eventually break. This is how entomopter joints behave. The force constantly changes direction, causing rapid wear. In theory, this problem could be partially mitigated by making the flapping mechanism more massive and using expensive materials. However, far more serious challenges remain: wing strength, rigidity, and vibration. For dragonfly-style flight, the wing must have almost infinite stiffness to minimize bending during motion. Any flexing reduces lift and can lead to wing overlap, which would have catastrophic consequences. With modern materials, it is impossible to create wings that are simultaneously strong, rigid, and lightweight. Even advanced composite materials cannot fully satisfy all 3 requirements at once. If we manage to meet only 2 of these conditions, for example strength and rigidity, the wings become heavy, and heavier wings require a much much more powerful engine. Highly inertial wings are extremely difficult to accelerate and decelerate dozens of times per second. Each flapping cycle requires stopping the wing's momentum, accelerating it in the opposite direction, and overcoming air resistance that can reach up to a quarter of the total mass of the aircraft. With heavy wings, it becomes practically impossible to do this fast enough. Another major issue is the energy source. While the transmission itself could take many forms, from linear electric motors to mechanisms converting rotational motion into linear motion, the power supply raises enormous questions. It would need to be extraordinarily powerful because the flapping cycle is very fast and the wings possess both high momentum and long leverage arms, making control extremely energy intensive. According to the most conservative estimates, the power source of such an entomopter would need to deliver 73 times more energy than a helicopter with the same passenger capacity. For comparison, the Tu-114 airliner can carry up to 220 passengers over a distance of nearly 9,720 kilometers. An entomopter with comparable energy consumption would be able to transport only 6 people over about 800 kilometers, requiring full maintenance after every flight. Economically, this makes no sense. Therefore, if such a compact and powerful energy system were available, along with an efficient high-speed transmission, it would be far more logical to use simpler vertical takeoff solutions, such as helicopters. Nevertheless, if we ignore economics, energy consumption, and structural limitations, the use of entomopters in the film Dune appears justified. Arrakis is a hot desert world dominated by vast sand seas beneath which roam enormous and aggressive creatures known as shaihuluds, highly sensitive to vibrations. The entomopter is equipped with 8 wings with a total span of about 40 meters. During flight, half of the wings move downward to generate lift, while the other half perform the flapping motion. This configuration helps reduce vibrations but introduces the risk of wing overlap. Additionally, the use of wings reduces ground erosion. In simple terms, they kick up less dust, which is important in desert environments. However, the film still shows clouds of sand during takeoff, and the entomopter lacks any visible dust protection seals on its wing joints. In reality, sand entering the joints would quickly disable the mechanism, especially under such heavy loads. The landing gear, shaped like insect legs, features massive supports designed not only to prevent sinking into soft ground, but also to dampen vibrations. Such a vibration damping system could significantly reduce oscillations during takeoff and landing, potentially lowering them enough that the giant shaihuluds would not react to the aircraft. There are no visible signs of a main power plant, either externally or internally. The only visible propulsion elements are a pair of small booster jet nozzles with an unknown energy source. The interior space of the entomopter is extremely limited. About half of its length is occupied by the tail, and roughly a third by the cockpit glazing. This raises the question of how 6 people, in addition to the pilots, could possibly fit inside. Under modern Earth conditions, creating such an entomopter is impossible, both in terms of structural strength and energy systems. Its economic efficiency is also highly questionable. Moreover, neither ornithopters nor entomopters offer any theoretical advantages over existing aircraft such as helicopters or vertical takeoff and landing airplanes. As a result, they are unlikely ever to be developed for military use, except perhaps as a few expensive prototype toys for the wealthy. For the conditions of Arrakis, aircraft such as the American UH-1 or UH-60 helicopters would be far more suitable. They have proven themselves in desert environments, are significantly cheaper to produce, lighter and more compact than ornithopters with a 40-meter wingspan. The only necessary improvement would be adapting their landing gear for sandy terrain. The vibrations produced by and detected by shaihuluds are high frequency, as these creatures use them to move through sand. Helicopters, however, do not generate such vibrations, making them more practical for use on Arrakis. Interestingly, Frank Herbert chose ornithopters because at the time he was writing Dune, helicopters were considered a technological dead end in aviation. Over time, that perception changed dramatically. I hope you found this analysis interesting. Share your thoughts in the comments, leave a like, and subscribe to the channel if you enjoyed the video. This was MiliTime Fiction. See you next time.